Okay, we left off at the frequency distribution, right? We calculated a weighted mean. We had taken a look at a GPA example, and there was also an example dealing with bank statements. Today we're going to take a look at the empirical rule, and the empirical rule is sometimes called the 68, 95, 99.7 rule. And what it means is that 68% of the data fall within one standard deviation of the mean. So if you look at this chart closely, right, notice that in the very center of this bell-shaped or normally distributed curve, we have X bar, which is the mean. One place to the right of the mean where it says X bar plus S, if we were to take the mean and add to that the standard deviation, that would give us one standard deviation above the mean. If we move one place to the left, we have X bar minus S, right? That doesn't make this negative. We're simply taking the mean and subtracting the standard deviation. This would be one standard deviation below the mean. So this empirical rule states that 68% of the data fall within one standard deviation of the mean. The 95 in the 68, 95, 99.7 rule states that 95% of the data lies within two standard deviations of the mean. Okay. And you'll notice that what we're actually looking at in the gray area is the area under that particular curve. So 95% of the data is within two standard deviations, and then 99.7% of the data fall within three standard deviations of the mean. You can only use the empirical rule if you have a bell-shaped curve. Right, so notice that this sort of looks like a bell, Taco Bell. This is a bell-shaped curve. You can also use the empirical rule if your data is normally distributed. So you're going to see words like bell-shaped curve, normally distributed, or a normal distribution. All of these things can require the use of the empirical rule. However, there are some curves that are not bell-shaped. We have some curves that are skewed, right? So if you take a look at the three examples here, the skewness lies in the tail. So what I mean by that is the skewness lies in the tail. Okay. So if you take a look at these three distributions, this first distribution, since it has a tail that falls to the left, this is considered a left skewed distribution. If we take a look at the second graph, notice that it has a tail to the right. That's considered a right skew. So notice on our bell-shaped curve, right, our bell-shaped curve is symmetric. And then we have something called a uniform distribution, and a uniform distribution is mainly flat across the top. For these three types of distributions, you cannot use the empirical rule. Okay. The empirical rule can only be used with the bell-shaped curve, normal distribution, or if the data is normally distributed. That should be normally distributed. Okay, this is the only uses for this empirical rule, right? Everything else, we're going to talk about the skew distributions in a later module. Now, as far as the empirical rule is concerned, I'm going to pull up the handout, and we're going to take a look at number 5. Right, number 5 says the Acme company manufactures widgets. The distribution of the widgets is bell-shaped. Right, so notice that the problem is telling us that we're dealing with the bell-shaped curve. The widget weights have a mean of 51 ounces and a standard deviation of 10. We're asked to use the empirical rule to answer the following. A says 99% of the widget's weights lie between what two values? B says what percentage of the widget weights lie between 51 and 61 ounces? C says what percentage of the widget weights lie between 21 and 81 ounces? And we're going to use the empirical rule to answer the following questions. Now, whenever you're asked to use the empirical rule, all right, this is mainly what I'm going to do. I'm going to use this empirical rule. Notice that it has all of the percentages, right? So 34% falls between the mean and one standard deviation below. You can see all the percentages on this chart. So it tells us that, and I'm going to just bring all of this up, okay? The mean is 51 and S is equal to 10. So I'm going to use those two pieces of information to fill out the baseline, right, or to figure out the values for these standard deviations above and below the mean. All right, so in the very center we have the mean, right, and the mean is 51. If I go one standard deviation above the mean, I'm going to take the mean, which is 51, and I'm going to add S. So S is the standard deviation, and S is 10. So 51 plus 10, that's going to give me 61. Now I'm going to go 2 standard deviations above the mean. So basically, I'm going to take the mean, right, which is 51, plus 2 times S, which is 10. So that's going to give me 51 plus 20, which is 71, right? And then I can use the formula, or since I know the standard deviation, I can just add the standard deviation. So 3 standard deviations above the mean would give me 81. Right? So notice that I have my mean, which is 51, and then I'm going by increments of 10 because 10 is the standard deviation. So now I'm going to find the values for the deviations below the mean. So instead of adding 10, I'm going to subtract 10. So 51 minus 10, that's going to give me 41, 31, and 21. All right. So any questions on where these values are coming from? We're simply taking the mean, and we're taking the standard deviation, and we're going forward. So we add the standard deviation. If you're going back, you subtract. So now these are our values. So with that being stated, let's answer the following questions. it says that 95% of the widget weights lie between what two values? Well, if I look at my empirical rule, and if I look for the 95%, notice that for 95%, it runs from 31 to 71. So between 31 and 71, we have 71. We have 95% of the data. B says, what percentage of the widget weights lie between 51 and 61? So if I locate my values 51 and 61, notice that 34% of the data falls between these two numbers. So B would be 34%. And C says, what percentage of the widget weights lie between 21 and 81? Well, if I look at my empirical rule, there should be 99.7% of the data that falls between 21 and 81. Right. So that's 99.7%. So anytime you're asked a question on using the empirical rule, I would pull out this chart and I would basically just lay out all the numbers. Okay, so using this chart, there's less and likely for you to make an error on finding these percentages. Okay? So as long as you know your mean and as long as you know your standard deviation, you can find the percentage between any values. All right, any questions about the empirical rule? All right, it's laid out with the mean and the standard deviation. All right, and just keep in mind that the percentages are located in the gray area. Question? Well, now the standard deviation was given to us in the problem. Right? It says that the mean is 51 ounces and the standard deviation is 10 ounces. So now in your problems, your mean and your standard deviation may be slightly different, but they must be given to you. Right? With those two pieces of information, you can, right, put your numbers on the baseline. So this is only applicable to bell-shaped curves. All right, if we go back to the pop up lecture notes if it wants to pop up. All right, there's something called a z-score. And a z-score is nothing more than a standardized value of the standard deviations that give the value x below or above the mean. To find a z-score, here is the formula. So this z actually stands for z-score. That's equal to x, and x would be your data value minus the mean. So this funny looking M that you see, that is a Greek letter of the alphabet mu. All right, but we're using that as the mean divided by the standard deviation. Now here's what a z-score looks like, and a z-score is a standardized value. So if I go back to the empirical rule, and I'm just going to erase these things. this down some. All right, so for a standard curve for z-scores, the mean is 0 and the standard deviation is 1. So that means the following. If you're asked to find the z-score, right, the mean is in the middle, that's 0, and my standard deviation is 1. So on my baseline, I'm going to have 0, 1, 2, and 3. And if I go to the left of our mean, I have -1, -2, and -3. So your z-scores, they range between -3 and +3. So we use the z-score formula to rewrite a data value as a z-score. So notice that z-score is going to fall between -3 and +3. Or we can convert a z-score to a data value. Okay, so I'm going to rewrite the formula for the z-score. So z is equal to x. So x is your data value minus the mean divided by the standard deviation. So that is the formula for a z-score. Now we're going to see how this actually works in an example. All right, so here is the example, and this is taken from the handout, and it's problem number 6, right? It says a normal distribution has a mean of 9 and has a mean of 127 and a mean of 9, and we're asked to find the z-score for a data value of 137. All right, so we're going to find the z-score. So I'm going to use the z-score formula. All right, so z is equal to x minus the mean divided by the standard deviation. So remember that x is the data value. So if we're looking at that normal curve, 137, that's going to be the value located on the x-axis. Right? Minus the mean. So the x is going to equal to 137. They give us the mean, which is 127. Divided by the standard deviation, which is equal to 9. So we're simply going to substitute those numbers into the equation, and we're going to find the z-score. Okay? And the z-score should range between -3 and +3. All right, so as we calculate this up, z is equal to 137 minus 127 divided by 10, divided by 9, because our standard deviation is 9. Now, once we simplify, 137 minus 127 is 10, divided by 9. And once we divide 10 by 9, I believe we get 1.11. So that means that the data value for 137 has a standardized z-score of 1.11. So here again, you can only use the z-score formula if you have a bell-shaped curve, a normal distribution, or if the data is normally distributed. All right, so that is the z-score. All right, so any questions about a z-score? All right, if I go back to the lecture notes, the next thing we're going to talk about is correlation. And a correlation exists between two variables when one of them is related to the other in some way. The linear correlation coefficient R, it measures the strength of the linear relationship between the paired variables. Sometimes that R is called the Pearson product moment correlation coefficient, but we're simply going to call it the correlation coefficient. Now, when we talk about correlation, we talk about two variables. Correlation does not represent like causation. We're dealing with two sets of data. One set of data does not cause the other set of data. So there is no causation between the two, but they may be related. Okay. So we're going to take a look at just what is a correlation and then what is this correlation coefficient. And then there's a problem on the handout that wants us to calculate this correlation coefficient as well as a linear equation. So this is going back to algebra more or less, but as far as algebraic equations are concerned, this is the only place where it pops up in this course. All right, so let's talk about correlation. And I'm just going to do this from the beginning. Correlation. All right, now and this is going back to algebra a little bit. When you read graphs from left to right just as you read sentences from left to right. So we're talking about linear relationships, so we're looking at straight line graphs. If you read a graph from left to right, and if that graph goes up, that is a positive correlation. It's like in algebra, this would be a positive slope, but in this course, we're more so worried about correlation. All right, so that would be a positive correlation. If you're looking at a scatter plot, and a scatter plot is nothing more than a plot of ordered pairs, and if that scatter plot appears to rise, that is a positive correlation. If you read a graph from left to right and that graph goes down, this is a negative correlation. Okay. So in algebra, if you were looking at or trying to find the slope of this line, the slope of the line would be negative. In this course, we're trying to find the correlation of a scatter plot. And if that scatter plot seems to go down from left to right, then it would have a negative correlation. And then if we have a flat line, right, if we were to look at a scatter plot and it doesn't look like it's going up, it doesn't look like it's going down, if everything is just sort of all over the place, then this would be no correlation. All right, so let's just take a look at some scatter plots. That's fine, that's fine. Okay. All right, so technically this stuff is on an X and a Y axis. So I am going to just construct the scatter plot. All right. So the main thing I want you to look at here, this is just a scatter plot, right? A set of X and Y ordered pairs graphed on an axis. If you were to read this from left to right, it looks like this scatter plot is doing what? It looks like it's rising from left to right. So this would be an example of a positive correlation. So let's take a look at another scatter plot. So let's say this scatter plot looks like this. So if you have a scatter plot that looks like this, as you're reading this scatter plot from left to right, it appears that this scatter plot is doing what? It's going down. So this would have a negative correlation. And then for the third, just take that one away. So if you look at this third example of a scatter plot, as you read it from left to right, it doesn't appear to go up, it doesn't appear to go down. Everything is just kind of in one central area going across. So this would have no correlation. So as far as correlation is concerned, we're looking at basically reading these scatter plots from left to right. Now on the handout, for problem number 7, right, it's basically asking us the same thing. It says, match each scatter plot shown below with its best description of its correlation. So if you look at this first scatter plot, is it no correlation, negative, or positive? Well, as we read it from left to right, that appears to go down, so that would have a negative correlation. If we look at the second example, as I read this from left to right, it doesn't appear to go up, it doesn't appear to go down, so this would be no correlation. And if we look at the third example, right, as we read this from left to right, it goes up, so this would have a what? Positive correlation. Now, to actually dovetail on that, on some problems, you will have to associate a number value with the correlation, and that's where the R value comes in. All right, so if I go back, and as far as correlation is concerned, R, it runs from -1 to +1. Okay, so I'm kind of writing this out mathematically, but R is less than -1 or greater than +1. You can't have any R values that are greater than 1 or any R values that are less than 1. So now here's what all of that means. Let's just say I have a scatter plot, right? And let's just say, for example, and this is not always going to happen in real life, if you look at a scatter plot, and if all of those lines, all of those points fall on one line, then you have the maximum positive correlation. So what I mean by that is, so take a look at the scatter plot. So notice I can draw a line of best fit or a regression line, and each one of those points fall on that line. My R value would be +1. The reason why it's positive is because it's a positive correlation. The reason why it's 1 is because the points fit either really, really close to the line or they fall exactly on the line, right? So that has a strong positive correlation, which means that both variables rise equally. So let's look at a second example. So let's just say we have a scatter plot, and if we draw a line of best fit, all of those points fall on that scatter plot. We would have a correlation coefficient of -1, right? Because all of those points fit tight to our line, right? So it's negative because the scatter plot is going down, and it's 1 because the points lie tight to that line. All right, now there is a problem in the homework that asks you for the correlation, and then it also asks for you to give a number value. All right, so I'm going to pull that up. I believe that's in section 1.8. And it is problem number 3. Right. So now, unlike the problem on the handout where it just asks you if it's negative, positive, or no correlation, this actually wants you to stick a number to it. So as I look at my numbers, I have negative 0.93, which is real close to -1. I have negative 0.37. Next, I have 0.98, which is close to +1. And then for D, I have 0.09, right? And it's positive and it's kind of close to 0. So now if I look at the scatter plots, this first scatter plot, should its correlation be positive or negative? It's positive, all right? The second scatter plot, is its correlation negative or positive? It looks like it would be positive or negative. All right. If I look at the third one, does that appear to be positive or negative? It appears to be kind of negative. And then if I look at the last one, this appears to be what? Negative. All right. Now, as far as the negative is concerned, or the positive, the 0.98, that would mean that that scatter plot should be rising from left to right. And since it's close to 1, my points should lie close to that line. So if I'm looking at my scatter plots, it seems like this first scatter plot, its correlation coefficient should be 0.98, right? Because I can almost draw a line through that scatter plot and every point is really close to that line, right? So that should be C, 0.98. Now let's look at negative 0.93, which is really close to negative 1. So that means if I'm looking at a scatter plot, that scatter plot should fall as I read it from left to right. And then since it's close to negative 1, that means the point should be tight about that line. Right? So as I look at my answer choices, it looks like that's going to be it, right? Because as I read it from left to right, it falls, and I can almost draw a line through those points, and the points are going to be really, really close to the line, but it's negative. So that would be A. So now notice what's left. I have negative 0.37. So that means if I'm looking at a scatter plot, it's going to go down, but the points may not be close to the line. If I look at D, 0.09, that's really close to 0. So let's see, if I go back here, so what would that look like? So let's just say if this were the scatter plot, and all of those points fit like a horizontal line, that would have a correlation coefficient of 0. All right, so going back to the homework problem. So now looking at this, I have what's left, negative 0.37, and that should fall down slightly. And then I have this 0.09, which is close to 0. So I'm probably not going to see it rise, or I'm probably not going to see it fall. Right? But as I look at the remaining 2 answer choices, which one do you think is going to have the correlation coefficient of negative 0.37? It looks like probably this one. Because if I look at my outermost points there, and then if I look at my points here, it looks like this thing is generally going down, right? And it's kind of hard to make out. A lot of these things are like subjective. So I'm going to say that this should be B. And then if I look at this one, it seems like this is kind of rising, right? This is not so much rising. So that's going to be close to 0. So this should be our D, 0.09. Right. Is everybody okay with associating a R value to a scatter plot? Now, if it's close to 1 or close to negative 1, those are kind of easy to discern. But if it's something else, you got to use like a little bit of judgment. All right. Are any questions about number 3? All right. Now, the last problem, okay, as far as the lecture notes are concerned, it cuts at correlation. But there is a problem on the handout. I'll copy that over. So just give me 1 second. All right, so you will see a problem similar to this on the test. And unfortunately, it is a calculator type problem. So if you have your calculator and you want to pull that out, and I'm going to reset the calculator. All right, so this is problem number 8. And it's a research example, and it says that research was conducted on the amount of oxygen runners could utilize during training, known as their VO2 max, and their finishing times for a 5K race to see if there was a significant relationship between the variables. So they're not saying that one causes the other. They just want to know if there's a significant relationship. So a significant relationship would be values for R that are either close to +1 or close to -1. So that's what they're alluding to by the relationship between the two. That correlation coefficient establishes a number value to that relationship. And we have 8 runners, and their data is compiled below. All right, so there's 8 runners. Each runner has their VO2 max, which was the amount of oxygen that they utilized during the training. And then for Y, right, because this is basically an X and a Y chart, we have their finishing time for a 5K run. So we want to know if the amount of oxygen that they utilized was related to their finish time. It says calculate the correlation coefficient, that's that R value. We have to find an equation of the regression line. So this is kind of going back to college algebra a little bit. And then it says predict the time in the 5K run for a runner whose VO2 max is 29.07. Now I'm going to go through this problem in class, but on the Blackboard homepage, I kind of posted this video a while back, especially dealing with the calculator. So if you want to go back and revisit the steps and how to solve the problem, because it's the exact same problem, you can just take a look at this video. It's not very long. I think it's about 10 minutes or so. All right, so going back to our window. All right, so first we're asked to calculate the correlation coefficient, and then we have to find an equation, and then we have to make a prediction based on that equation. So the first thing we're going to do is enter the data into the calculator. We're going to put in the VO2 max as list 1 and the finishing time as list 2. All right, so I'm going to turn my calculator on. So in order to put this data into the calculator, I'm going to hit Stat. I want to choose Edit. And from this point, I'm going to put in the VO2 max is L1. The finish time is L2. So I put Stat. And then we hit Edit. And then I'm going to put in the VO2 max is L1. So now if you have data that's already in your calculator, right, in order to quickly clear that out, you can go to the very top of your list. You can then hit clear and enter. And that would wipe out your entire list. So since we're going to use L1 and L2, you just want to make sure that those things are clear. So now I'm going to put in my data points. So let me just check what I have. All right, so I'll give you a minute to put that in. All right, so the next thing we're going to do is return to the home screen. So I'm going to use second and mode, all right, which is that quit key, right, that you see on my calculator is yellow. On your calculator, it may be blue. So I'm going to hit the second function and mode, which is the quit key. And that returns us to the home screen. Okay. Remember, you perform all your calculations on the home screen. All right, so now what we want to do is calculate the linear regression equation. Okay. Now, before we actually do this, we got to put the, okay, well, we'll just do it this way. Okay, calculate the regression equation. So I'm going to hit stats. I'm going to scroll over to calculate. I'm going to scroll down to linear regression AX plus B, which is the for function and I'm going to hit enter. Now, it may look different if you have a TI-84. I think you see something. What's the first thing that you see? What?
It says like the X list.
Okay, X list should be L1. And then it has Y list. Okay, put L2.
And the frequency list is blank.
Okay, frequency list. Okay, leave that blank.
And then it says store.
Leave store blank. And then it says calculate, right?
Yeah.
Okay. Okay. So is everybody following along? Okay. Were you able to put the data set in? Okay. Oh, I got you. Okay, let's put it. So go back in the step. Now you want to scroll over to the right. And now scroll down to linear, that fourth option. And now you show, that's what I have on your camera.
Yeah, so I hit calculate. Yeah,
That's it. That's it. So once you hit, okay, enter once. Once you hit enter twice, this gives us the linear regression, right? Why? Now, for some strange reason, like in algebra and through all the textbooks, the equation for a linear equation would be y is equal to mx plus b, where m is the slope, b is the y-intercept. For whatever reason, when they program this calculator, instead of choosing m, they choose a. Okay. So this actually gives us an equation. Now, on some calculators like the TI-84, you probably see an R squared and an R value, right? This is how you turn these things on, okay, especially if you're dealing with this TI-83. So once you go through this process, the next time you calculate the linear regression, it's going to pop up an R squared and an R. So if you don't see those values, if you just see A and B, then you want to do the following. Okay. And let me just make a note of this. To calculate R, and you only have to do this one time. And from this point forward, when you calculate a regression equation, it's going to pop up the R value. You have to turn these your diagnostic on. So I want to find catalog, right? And on my calculator, catalog is above 0 and it's yellow. So I want to hit second and 0, which is catalog. Once you're in the catalog, you want to scroll down to the D's and you want to look for diagnostic on, which is here. On some calculators it's set, I think on the 84 it's set to give you the diagnostics, but if you have a TI-83 or TI-83 Plus, you have to turn them on. And once you turn this on, then you have to manually go in and turn it off. So you only have to go through this process once. So now that I see diagnostic on, I want to hit enter once. And now it says diagnostic on, which is on my home screen. And if you hit enter again, it just says done. Right? Like it really hadn't did anything, but it actually has. So now you only have to go through that process once. second and 0. So the second and 0. Scroll down to the diagnostic. Okay. Were you able to turn yours on? Or did it already pop up? Okay. Were you able to? Okay, you got the diagnostics on. All right, so you only have to do this once. So now I'm going to just clear my home screen. So I'm just going to hit clear. So I'm looking at a blank home screen. And then we're going to calculate that regression equation again. But this time we're going to see some additional bits of information. So in order to calculate that regression equation again, I'm going to hit stat. I'm going to scroll over to the right to calculate. I'm going to scroll down to the fourth option, which is linear regression, AX plus B. I hit enter once. I hit enter twice. So notice we see some additional bits of information. We see an R squared value and we see an R value. That R value that we see, that is the correlation coefficient, right? And it gives us the strength of the relationship between the two variables. So does everybody see this output on their screens? Now from this, we're going to formulate, well, we can actually answer the first question. The first question says, calculate the correlation coefficient around the 3 decimal places. So I believe that's going to be negative 0.911. So in order to round to 3 decimal places, you find a number that's in the 3rd decimal place. You look one number to the right, and if that number is 5 or greater, you're going to round up. So our R value is negative 0.911, which is really close to negative 1. So that means that there is a strong negative relationship between the two. So what that means is that once one goes down, the other goes down. All right? So I don't really ask you that in the question, but that's what the negative means. Both variables go down at the same time and about the same rate. The next question says, find the equation of the regression line. Round each value to 2 decimal places. So this would be our equation, right? Y is equal to AX plus B. I'm going to simply substitute A for negative 0.55 on the negative 0.455. I'm going to just write that down here. So our equation is Y is equal to negative 0.455x plus B. So I'm going to put my plus. and B is 43.899. So this is going to be 43. Okay, it says round to 2 decimal places. I'm sorry. So our equation is going to be negative 0.45x plus 43.9. So in order to round to 2 decimal places, I found my second decimal place, which is 9. I look 1 to the right. That rounds that 9 up, which rounds the 8 up to 43.9. So this is the regression equation. Any questions about how to calculate R and how to calculate the regression equation? Now, there's other problems in this homework set that require you to do the same thing. You just put the X in list 1, you put the Y in list 2. You can calculate the linear regression, and then as you're calculating that linear regression, this R from this point forward will automatically pop up. As you turn the diagnostic on, the only way to turn it off is if you physically go in and turn it off. All right, so now there is one last piece of the question. It says we have to use that equation and we have to predict the time of a 5K runner whose VO2 max is 29.07. So remember this equation, it actually means something, right? Remember that X and the values we put in for X was the VO2 max, right? And then Y, I remember that our Y variables were the 5K finishing times. Right? So what we're asked to do, we're asked to predict the 5K time based on a runner whose VO2 level is 29.07. So what we have to do is take this equation and we have to substitute X for 29.07. So now if it were asking for the VO2 level based on the running time, you would have to substitute in the value for Y. Right? So remember, what you put in for X and what you put in for Y, they still mean the same thing after you calculate this equation. Right? So from this point, I'm just going to substitute X for 29.07. Right, so I'm going to put this in as negative 0.45 times 29.07. And I'm going to close that parenthesis. So now the calculator understands parentheses as multiplication. All right, so I put the 29.07 in a set of parentheses plus 43.9. So a runner whose VO2 max is 29.07 would have a finishing time of 30.82 minutes. So Y is equal to 30.82. So the answers to these questions are, you just write them in. y is equal to negative 0.45x plus 43.9. And for the last one, where it asks to predict the time for the 5K runner whose VO2 max 29.07, we get 30.82 minutes. All right, so a little bit, almost half an hour to finish a 5K race. All right, any questions about number 8? I know we went through some things with the calculator, but keep in mind on the home page, right, I actually go through that same, the 6 minutes and 49 seconds, and I actually go through the same exact problem, just showing all the